So I'm going to talk a little bit, I don't know why that showed up that way, but anyway, I'm going to talk a little bit about basic science at Jupiter, and then we'll have Jim Tiemann and I will have a second talk on a little bit more advanced stuff. But this is for some of you who maybe never observed Jupiter, or maybe don't know that much about it. So I'm sort of starting very basic here. And I want to talk just a little bit about basic Jupiter facts. You know, how does Jupiter compare? What's the internal structure look like? What do we know about Jupiter? Some basics. Talk about the magnetosphere, and then I can't play you any sounds, unfortunately, Jupiter sounds, but many of you have heard them before. We'll have demos later tonight for it. And then talk a little bit about how Io interacts with Jupiter and how that affects the radio waves that we receive, and then a little bit about the emission mechanism. So our friend orbits at 5 AU from the Sun and has an orbital period of almost 12 years, 11.9 years. Some fun facts about Jupiter here. You can see the scale, overall mass and size compared to the Earth. Its atmospheric temperature, of course, is quite cold out there. It's very low density. The Earth is 5.5 grams per cubic centimeter density. Jupiter and the other gas giants are much, much lower because they're gas giants. So gaseous planets, the average density is not much above water. The tilt of the axis is a little over 3 degrees, and that's the rotation axis. The rotation period, I didn't mention this yesterday, but we use the radio measurements of Jupiter coming from the magnetosphere as our way to measure the rotation period of the planet. And that's what I did for my thesis at the University of Florida. So that was part of my thesis presentation. The magnetic field of Jupiter you see there and listed in Gauss. So at the equator, 4 Gauss. North and south pole it's offset, so the northern hemisphere of Jupiter has a little bit stronger magnetic field, and you can compare this with Earth is just a little less than one Gauss for the global field. The internal structure, so it's got a pretty thin atmosphere, but very quickly below the atmosphere the pressures get high enough that the mostly hydrogen and helium, becomes liquid. And then as you get deeper and deeper into the atmosphere, that liquid, the pressures cause that hydrogen to, the extreme pressures cause hydrogen to be rendered into a metallic state. So we say metallic hydrogen. So we know metals have that one valence electron that allows it to electricity to conduct. So hydrogen has 1 electron. So under the right conditions, it is in a metallic state, so it conducts electricity. Why is that important? Well, in order to generate a magnetic field, you have to have a moving, electrically conducting material. So now we have an electrically conducting material in this metallic hydrogen. And we've got a fairly fast rotation, 10 hours. So there's a lot of energy in that rotation. And there's also convection going on. It's the same as the Earth. So the Earth's magnetic field is generated by the liquid nickel iron layer in the outer core, spinning planet, electrically conducting material that is convective, then sets up moving electrically conducting material will set up a global magnetic field. And there's a very weak global field at Mercury, slow rotator. No global field at Venus, basically very slow rotator. No global field at Mars, because the interior is not molten. There may be some partial melted regions in there, but there's only some regional fields at Mars. So you have to have this dynamo mechanism set up by this moving electrically conducting material, and Jupiter certainly has it. As I mentioned, the atmosphere is 99% hydrogen and helium, the same as the Sun, the same as other stars, the same as our galaxy, the same as the universe, right? The universe is 99% hydrogen and helium, 99.9% hydrogen and helium. Everything else is just very, very, very small part of the universe. And at Jupiter, we have pretty good signatures of water, methane, ammonia in the form of liquid, and then also ice clouds. And we have a pretty good profile, at least of the upper atmosphere now, due to the Galileo probe that parachuted through the upper layers of Jupiter. And so we have this profile of the atmospheric structure. And Jupiter has a ring system, which most people don't know. We didn't know until the first spacecraft flew by. So it's a very thin ring system. That's a beautiful picture there, silhouette from, I forget if that's Galileo. I took that, I believe so, looking back, where kind of an eclipse from the sun. The 4 Galilean moons, and our own moon to scale, just to give you an idea. So Io, the innermost Galilean moon, is constantly volcanic because of the tidal energy caused from the interaction with caused from Jupiter. So the orbit, due to gravitational effects from Europa and the other moons, causes Io to orbit to be slightly non-circular. And this tugging from the other moons and Jupiter causes large tides on the moon. And the way gravity works, the tidal force is it's a differential force. What that means is it likes to squeeze the planet, or the moon in this case. And so you can imagine this moon being squeezed, and then as it moves away, then it's unsqueezed and squeezed and unsqueezed. So the same as our water here on Earth is being squeezed, and the water develops 2 bulges at the equator, so you have 2 high and 2 low tides per day. So you have a similar effect on Io, but the greater mass of Jupiter, of course, you get a molten interior. So all that energy melts the interior of Io, and therefore it's constantly volcanic. And so that was predicted back in the 60s, believe it or not, and then confirmed by Voyager in '79 that Io is indeed volcanic and constantly volcanic. So, and there are some images of some of the hot spots from volcanoes at Io at night. And so why is that important for us? Because the interaction, the plasma interaction with the moon Io and Jupiter, the magnetosphere, that is a source of plasma. So an astronomer and a graduate student in the mid-50s were trying to observe the Crab pulsar. And in doing so, they kept getting some interference, what they thought was interference, at multiple nights. And they went back and looked at their records and realized that this interference was drifting in time at the sidereal rate, right, at the star rotation period. the sidereal rotation of Earth. So this is star time, essentially. And so they went back and looked, and the only thing that was in the beam of the antenna at that time was Jupiter. So they realized that they were actually observing signals from Jupiter. And I do not know, maybe somebody in this crowd knows, why were they observing the crowd, I think at near 20 megahertz. I don't know that history, but I guess it was fortuitous, and they picked up the signals from this Mills Cross array in sort of northwestern Maryland. And they announced it in April of 1955, and then soon after at an American Astronomical Society meeting. And Leonard Garcia, the archivist for Radio Jove, really took it upon his shoulders. He wanted this site recognized, that this was a major discovery, and so he, through the Cultural Center department, I'm not sure what department you go to do this, but he had a sign erected, a road sign there, which marks the site of discovery, and so you can drive down River Road near Potomac, Upper Potomac, and you can see where we discovered Jupiter radio signals. And here's a few key dates. I won't go through all of these, but just some discoveries that were made, important ones. And I like to show this image because it really gives you a perspective, a scale perspective on how big Jupiter's magnetosphere really is. So there's the Sun in the upper right, and then the Earth-Moon system. Again, all to scale, so you can get an idea that the magnetosphere would be 4 times the size of the Sun, 4 times the diameter of the Sun, to scale. And the whole thing is tilted 10 degrees, right? So its magnetic axis is tilted about 10 degrees off its rotational axis. And about the same time we were discovering or confirming that the Earth had radiation belts with the Explorer spacecraft flying through them, so making in situ measurements here, we made measurements of Jupiter's radiation belts. So it's basically the same year. And much to the chagrin of scientists at the University of Florida, the influence of the moon Io on the radio emission was discovered by, I think, an Australian, right? Is it big as Australian? Is that right? Yeah. Yeah. So, and then later, Aurora was discovered by the spacecraft, and then smaller influences by some of the other moons came after the Galileo mission. Just another view of Jupiter's magnetosphere. This is a synchrotron image, so 13 centimeter measurements of Jupiter's magnetosphere, and here you can actually see the radiation belts there. And then this is the plasma that makes up we call the Io torus. So Io being volcanic and orbiting around Jupiter about once every 42 hours. That material which gets thrown into the magnetosphere will get quickly ionized. So it's neutrals. They get quickly ionized by the solar ultraviolet light. And then Jupiter then, that material then is sort of locked into the magnetosphere, which is also rotating with Jupiter about every 10 hours. So that plasma gets pulled around into a big donut at the orbital position of Io. And I'm sorry, a couple of the movies that I was supposed to check on and make sure I had working, I didn't, so they're not working. But anyway, just another graphic showing you some of the plasma. So this is sulfur at Io. So sulfur ions, I should say, at Io. And it's mostly sulfur compounds, and then there's oxygen and some sodium that are spewed out of these geysers and volcanoes, I guess, if you want to call them that, on Io. Just another picture of the magnetosphere. Now this shows you the tail. So the solar wind will cause the magnetosphere to be stretched in the anti-sunward direction, and then see, just from what you've heard now, you can imagine how dynamic this whole thing is. So you've got Jupiter spinning, you've got the magnetic field, you've got plasma. So where does this plasma go? How does it move? Well, it's sort of moves out radially along what we call a current sheet, and then it gets closed back. So it forms a kind of a current loop there. It gets closed back to the ionosphere along magnetic field lines, and then that's part of how the aurora works at Jupiter. But this again just gives you a scale of where Io is in the torus and where the other Galilean moons are compared to Jupiter. So as I mentioned, aurora were discovered by Voyager in '79, and then this shows you some really nice Hubble images in ultraviolet light of the aurora. So they work the same way on Jupiter as they do here on the Earth, and these are highly connected with the radio emissions as well. So sort of the same reason we get auroral emissions, we get the radio emissions. This is a really cool picture. It's kind of famous now. I think everybody shows it. But not only do you see the auroral oval and a lot of structure in the aurora, you see what we call footprints. So this is the plasma that kind of moves along magnetic field lines that pass through Io and the Io torus. So that moving plasma actually makes a signature in the ultraviolet here in the upper atmosphere of Jupiter. So you kind of have an aurora due to Io. And you can see, not only can you see where the footprint is, but you can sort of see the trail as Jupiter rotates and pulls that plasma with it. So it's exciting the upper atmosphere. That plasma is exciting the upper atmosphere as it moves down magnetic field lines. And you get to see there was one at Ganymede and one at Europa that was identified. Really amazing. The Callisto footprint should be there as well, but it's probably buried in the main oval, and you can't detect it. At least I don't think we've detected it. So this is where I was going to play a couple of sound files for you, which I don't have. I apologize for that. You have to see Francisco and Dave and Wes tonight after dinner out in the lawn. They'll play it, and we may play some of these tomorrow as well. So Jupiter has two basic kinds of bursts. We call them L bursts or long bursts. So it's swishing emission. So you've got the continuum, you've got the galactic background, and then you get these bursty swishes or waves sort of sounds crashing. And that is coming from Jupiter's magnetosphere and being modulated by interplanetary space. So that's why you get the sort of the bursty nature in part, and the ocean waves crashing sort of structure. So that's the long bursts, which are hundreds of milliseconds to seconds in length. And then you have what we call the short bursts, S bursts, which are hundreds of microseconds to few milliseconds in length. So very, very short bursts that are maybe 10 to 100 times stronger signals. And those sound like pops or popcorn popping in a microwave, or the sound of raindrops fell and they had, they were made of BBs on a tin roof. That's sort of what it sounds like. We can slow these sounds, or record the data at high speed and play them back at very slow speeds, and then you can actually see on a spectrogram the spectral signature of these S-bursts. And they move from high frequencies to low, and what's interesting about that is that ties into how the emission is being generated at Jupiter and where it's being generated, which I'll talk about here in just a moment. So since the mid-50s, people have been recording the signals from Jupiter and tying it back to the longitude system. Okay, so trying to organize the data to see if we can figure out what is causing this stuff. Why is Jupiter doing this? So the longitude system we use is called the central meridian longitude. So essentially, what part of Jupiter's disk, the central part of the disk, is facing you, the observer. And so we define a start date and start point, and we're going to call that 0. And then every moment after that, Jupiter's going to rotate at this rate, and then where you're observing Jupiter, wherever that longitude is facing you, that's the longitude that you use. You can't use the cloud tops, you can't use the red spot or anything else as a longitude marker because they're all moving. So we use the radio rotation period as our standard longitude. So we can plot these data as a probability of observing Jupiter, so you don't get it all the time, as a function of the longitude, and we get 3 main peaks, A, B, and C here. And you can imagine those are tied to the magnetosphere of Jupiter. So they're spinning around and emitting radio signals. Sometimes they do, sometimes they don't. It's very a dynamic and bursty structure there, but we can plot these. This happens to be a data from the early 60s. How likely is it to observe Jupiter signals? So over time we build up this probability map, and we can pick out the best times or the likely times when Jupiter will be emitting radio waves that we can pick up. This video I don't have working, I apologize for that, but you can think about this as a 3 megaphones tied to Jupiter, and as Jupiter spinning around, when those megaphones are pointed at Earth, we pick up or have a higher probability likelihood of picking up a radio signal. So the sources are tied to Jupiter, tied to the longitude in this case. And on top of that, there's this influence of the moon Io. So now, not only is it tied to the longitude, so which direction is Jupiter, oriented from your point of view, and where Io is in its orbit. So we now make a more complicated map here, where we're showing the orbital phase of Io from 0 to 360, and then the central meridian longitude, 0 to 360, although we offset it just a little bit here. And then you see these regions where Jupiter emits or has a higher probability chance of emitting. So around 270 degrees, no matter what the phase of Io is, you get higher probability chance of picking up Jupiter signals. But when Io happens to be in sort of 2 special locations, you get a much, much higher probability of receiving Jupiter. And the 2 sort of magical places are when Io is on the eastern side from your point of view, and almost on the western side. So at 90 degrees phase or at 240. And that is, let me go forward here. That then allows us to make a picture and tie it in with the theory as well of how this emission is beamed, how is it being generated. And the idea here is that it's a hollow cone. So electrons are moving down magnetic field lines. So it's electromagnetic forces that are causing the electrons to spiral. And the ions are doing this too, but there's so few and they're moving much more slowly that it's really the electrons that are doing all the work. So these electrons are moving down field lines, and in doing so, they are due to the influence of the electromagnetic forces on them, they're caused to spiral. So as these electrons spiral down the field lines, they're accelerated, and then when you accelerate a particle, charged particle, it will emit energy. In this case, it's emitting energy in the radio part of the spectrum, and it depends on the plasma conditions as well. But tied to a magnetic field line, then you have this cone of emission where the radio waves are emitted. Okay? And we have many cones, and they are tied to different wavelengths or different frequencies. So some of them are directly related to IO, so we call these the IO-related sources, and DAM there means decametric radio emission. We have the non-IO, we're very clever with our names here, but so this is the IO-related sources, these three high probability zones, and then this region here is a non-IO related zone. But we think they all sort of work the same way, that when these electrons are accelerated down these field lines, then the radio waves, so you're converting, it's kind of complicated, but you're converting then a moving charged particle, so from that moving charged particle to a wave. So you're converting energy from particle motion to waves, right? EM wave, electromagnetic waves. And they're sort of beamed out in these patterns. So now you can imagine if Jupiter is here and Io is out here, and there's a cone, this hollow cone. When Io is over here, the hollow cone is pointed towards the Earth, one edge. And then as Io slowly moves around, and when Io is kind of on this side, then you have another edge of that cone pointed in your direction. So that increases the probability that you're, the chance that you pick up a decametric radio signal. So, and we have cones in the northern and the southern hemisphere. So very quickly, how do we generate radio waves? Well, you can do it two ways: thermally, non-thermally. What is thermal radiation? Black body radiation. Everything that's got a temperature above absolute zero is emitting thermally. Well, can you emit radio waves at Jupiter via thermal, using thermal energy? The answer is yes, but as most of you know, that you've got to get something extremely hot, because of these black body curves, when you go out here to radio waves, way over here, something at 5,000 Kelvin or 6,000 Kelvin, a solar, this as hot as the sun, is going to emit basically zero radio waves thermally. You've got to get something to millions of degrees before it's going to be hot enough to emit enough radio waves. So you can do it as black body, you can do it where ions and electrons interact with each other, and we have Bremsstrahlung radiation, or you can do it spectrally. That's all sort of thermal mechanisms. Or you can do it non-thermally. So that's the charged particle motions in magnetic fields then emit energy, as I said, in a conical pattern, and it's amplified in this way. So you get groups of electrons, and sort of like a laser works, where you have stimulated emission, all coherent. You get the same sort of mechanism at Jupiter, but now it's in the radio, so we call it a maser type mechanism. But so you get highly beamed energy, and so that allows you to sort of pick up these signals from the Earth, from a distant source. So the cyclotron, synchrotron, spiraling, moving charged particles in magnetic fields is the reason why the emission is so strong. And getting back to calibration, so why do we test a receiver, compare it to a noise source, which is a resistor, right? A hot resistor. So we understand the non-thermal mechanism with what we really understand, the thermal energy. So black body energy. So we can compare what we get non-thermally to what we would get if it was thermal. So when you calibrate your radio signals, you're getting a Jupiter pulse or a solar burst that might be millions of Kelvin. So that's how hot Jupiter would have to be to give you the same signal thermally. So that's how it's all sort of tied together to the basic physics of how thermal and non-thermal energy works. So let me skip that. Tomorrow we'll get into more of the fine structure. So this is the spectrograph, a sample spectrograph of Jupiter showing an event due to IO. We call it IOB, but there's a lot of substructure in the data. So we'll talk a little bit about that more tomorrow. But so we've already talked about the L and S type bursts, but we can make measurements of polarization and learn more information. We can study these, we call modulation lanes, and learn something about the source and the propagation path. We can study other spectral signatures, and again, keep learning more and more and more about how this works, right? So let me just stop here, and I'll just leave the summary up there and take some questions if you have any, and we'll try to get Jim Sky up here and get you to lunch on time. Thank you.